Let's do one more example and demonstrate our z arbitrary. So let's say we have this equation of systems and maybe we find it really easy to get rid of some z's. I'm going to use equation number 1 twice. So I'm x minus 2y minus z is equal to 8, and x minus 2y minus z is equal to 8. I'm going to use equation number 2 over here, so that's 2x minus 3y plus z is equal to 23. And over here I have 4x minus 5y plus 5z is equal to 53. So maybe we find that we want to get rid of x's, but to do that all we have to do for this first set is just to add these two equations, and we'll see that the z's will zero out. So when I do that, I end up with 3x minus 5y is equal to 31. Over here we're going to find that we're going to need to multiply this times a positive 5, so that way I'll have negative 5z and a positive 5z, and those will zero out. So I'm going to multiply and get 5x minus 10y minus 5z is equal to 40. And down here we're going to have 4x minus 5y plus 5z is equal to 53. And now I can add these two equations and know that the z's will zero out. I'll get 9x minus 15y, that's gone, and I get 93. So now I have a two-equation system. The two-equation system consists of 3x minus 5y is equal to 31, and 9x minus 15y is equal to 93. So maybe we would say, okay, let's multiply this times a negative 3. That will give me a negative 9, and it will cancel out with this 9x that we have here. So here I am. I'm just going to rewrite it. Let me add a little bit more room. So we're going to say that we have a negative 9x, a positive 15y, and a negative 93. That's for multiplying that negative 3 times everybody. And I have my 9x minus my 15y is equal to a positive 93, and when we add, we're going to get 0 is equal to 0, which tells us that this is a consistent dependent system. We're not surprised because I told you that this is what we were going to have. So now the question is, how do I write this in z arbitrary? So what we want to do is we need to get two equations that have z in them. So what we're going to do is we're going to grab equation 1, x minus 2y minus z is equal to 8, and I will get 2x minus 3y plus z is equal to 23. And I'm going to do the same thing over here, except this time I'm going to have x minus 2y minus z is equal to 8. Notice I have equation number 1 written twice. Again, I'm going to go with my equation number 3, which is 4x minus 5y plus 5z is equal to 53. And what we want to do is we want to get rid of x in one equation and get rid of y in the other. So for this one, I'm going to get rid of x. So we are going to multiply this top equation by a negative 2, and that will see that negative x coming out. So let me multiply so we can see that. We're going to get negative 2x, positive 4y, positive 2z is equal to negative 16. This should look familiar to what we did above. Down here we would have 2x minus 3y plus z is equal to 23. And then now we can add them, and we're going to find that our x's will zero out, which we're not surprised because that was the whole purpose, to get rid of x's. And we'll find that we have y plus 3z is equal to 7. Over here, since we got rid of the x's, we need to get rid of y. So I'm going to write that down. Get rid of the y values. So again, we're going to see that I have a 2 and a 5. So I'm going to multiply the top one by negative 5. And I'm going to multiply the bottom one by positive 2. When I multiply the negative 5 times the negative 2, that's going to give me a positive 10y. And when I multiply the 2 times the negative 5y, it's going to give me a negative 10y. So when I add them, they will zero out. So now let's multiply and get a new set of equations. So this top one will become negative 5x plus 10y plus 5z is equal to a negative 40. The second equation will become 8x minus 10y plus 10z is equal to 106. And then we're going to add. We know, and to no surprise, that our y's will zero out. And when we add, we're going to get 3x plus 15z is equal to 66. Now we have an equation that only has x and z involved, so we're going to solve for x. And this will give me a function of x in terms of z. So when we do that, I'm going to get 3x is equal to 66 minus 15z. And notice, now when I divide by 3, we're going to see that it reduces for me, and we get x is equal to 22 minus 5z. We're going to do the same thing over here. We're just going to solve for y. When we solve for y, we find y is equal to 7 minus 3z. So last but not least, we're going to see that we have a value for our x. That's this equation that we found. We have a value for our y in terms of z. That's this one right here. And then we have z arbitrary. I wanted to show it to you like this just to realize that should you go all the way down where it says 0 is equal to 0 and you find a consistent dependent system, then you can go back and start doing this part again so that you can come up with two equations, one for y and one for x, so that you can have z arbitrary. What does this mean is that if we pick if we pick z is equal to 0, we can find the point 0 for z, 7 for y, and 22 for x. I just plugged in 0 for my z's. I can do the same thing here when I plug in 1. So z is equal to 1. So I'm going to do 22 minus 5 is 17. 7 minus 3 is 4. And then z was already equal to 1. So these are points that are on that line that all of these three planes have in common. And that concludes this video.